Hey guys, Professor Dustin here, and this video is going to be about uniform circular motion. So circular motion, meaning an object which is moving in a circle, or at least part of a circle, and uniform here means at a constant speed. So there's a few relationships that we want to know for objects which are moving in circular motion. So I'm just going to start writing down some things we might know because the object is moving in a circle, right? If it's moving in a circle with a radius r, we know how far it travels every rotation. If it travels from here around back to the original point, that's traveling in the circumference of a circle. So we know the distance that the object travels in one rotation. That will just be 2 pi times the radius. Okay, if this is moving at a constant speed, we know the speed, we'll call it v. The speed is going to be defined as the distance divided by the time, which is the definition of speed. So in one rotation, the distance this object travels is simply d, the circumference we have right there. But what do we call the time period that it takes for an object to start at one location and go all the way back to that original location? That's called the period. So the period of a motion that repeats itself is how long it takes for the object or system to return to the original state. So if an object starts here, the time it takes for it to return to the original point is the period, and I'm going to call that period capital T. So in my definition of speed, I have the speed is the distance divided by the time it takes to make one rotation. That's the period. So d divided by t. So if I plug this into here, I have a nice relationship between the physical size of the circle, the radius, and the period that it takes for the object to go one time around. So that's a simple relationship that happens in uniform circular motion and is special to uniform circular motion because we know something about the geometry of the system. There's a more complicated relationship which has to do with the acceleration of the object.
So here's a picture of an object moving in uniform circular motion. If you want, you could think of this as a ball on a string, which I'm swinging around in a circle, or a car driving on a perfectly circular track. Whatever it is, it's an object which is moving at constant speed in a circle of a specified radius. So the first thing we might think when we talk about the acceleration of such an object is, okay, it's moving at a uniform speed. So we might think, oh, okay, uniform speed, constant motion, that means the acceleration must be 0, right? Well, we have to be very careful with that kind of logic because speed is a scalar quantity. It's just simply a number, whereas acceleration is a vector. So if we have a case where the magnitude of the vector is not changing, meaning that the speed as the magnitude of the velocity is not changing, does that necessarily mean that the vector acceleration is 0? And in fact, that might not be true. We can see that very simply in the case of the circle. If we think, oh, okay, at one moment, the velocity of this object is pointed in this direction because that's the direction of motion. Sometime later, say right here, the object will be in a different location in the circle. What's the velocity of the object at that point? It's down in that direction. So although the magnitude of those two velocities is exactly the same because they have to be moving at a constant speed, their direction is different. Since their direction is different, it means that this can't be true, and we cannot assume that the acceleration is going to be 0 in this case. In fact, what we're going to need to do is figure out a relationship which tells us what the acceleration is in a similar way that we just found a relationship for the speed, period, and size of the circle. We want a similar relationship for the acceleration. So to do that, I'm going to start with my object right here with a velocity v1, which is going to be tangent to the circle. After some time period, that is however long it takes for the object to get from here to there, the new position of my object will be right here, and it will have a new velocity, which is now directed along the tangent to the circle right there. Now remember, the magnitudes of these two velocities have to be the same because I'm moving in uniform circular motion, but their direction is absolutely different. This one is this way, and this one is this way. So I can ask, what acceleration caused the velocity to change from being directed in that direction to being directed in this direction? Well, if I just use the definition of acceleration like this, the change in the velocity divided by the change in time, the change in velocity, the final velocity was v2, the initial velocity was v1. So the acceleration would just be the difference in the velocities divided by however long it took for that motion to happen. I have a nice picture here with the actual arrows that represent the vectors of these two velocities, so why don't I just subtract them like that? So I'm going to take v2, I'm going to add the negative v1 to it. So remember, when I add vectors, I have to add them head to tail. So I'm going to take v2, I'm going to take v1, put it head to tail, but then flip the direction because I have a negative sign. So that vector represents negative v1 added head to tail. The result, if I divide by the time, is the acceleration vector. So the result is right here. That is my acceleration vector. So I just determined that by thinking about how the motion in the circle is happening. The final velocity was this, the initial velocity was this, so I added the negative to it. Divide by the time, I don't know what the time period is, but at least this tells me the direction of the acceleration. The direction of the acceleration is apparently like that. I'm going to do this one more time. After the same time period, my object is now right there. My velocity is again directed tangentially to the circle. The acceleration can again be found just by taking the final minus the initial, v3 minus v2 now. And so I can find the acceleration at that point being directed like that. Again, I don't know the exact size of the acceleration because I don't know the time interval delta t, but all the directional information is in the change in the velocity. So you can probably see the pattern that's happening here. I'm going to fill in a few more of these calculations so you can see it better. And we should be able to describe the direction of the acceleration in a pretty concise way if we just observe that all those acceleration vectors appear to be pointed towards the center of the circle. In fact, towards the center of the circle, we have a special word which means towards the center of a circle, and that is centripetal. So the reason why we connect uniform circular motion and centripetal acceleration is in uniform circular motion, the acceleration is directed towards the center of the circle, and we call it centripetal acceleration. So that tells us the direction. I'm not going to go through it in this particular video, but we also can say something about the magnitude of the acceleration. The centripetal acceleration is often denoted AC, and in magnitude it takes on a very special value, and that is v squared over r, where v is the speed of the object. Remember, in uniform circular motion the speed is constant, so this v squared is going to be that speed squared divided by the radius of the circle. If we want to write that acceleration as a vector, we can do that. So obviously we don't really want to use an xy coordinate system or a Cartesian coordinate system to describe the radius vector, because the radius vector is always changing in the Cartesian xy coordinate system. In this right here, it's directed kind of into the xy, sort of first quadrant, but over here it's directed into the second quadrant. Over here it will be in the third quadrant. It will be constantly changing. But if we use a radial coordinate system, that is with the r hat vector directed radially and the theta vector being directed around the circle, we can actually write the centripetal acceleration pretty easily if we notice that the radius vector here is pointed in that direction, the acceleration is opposite that direction. So the appropriate way to write it is negative v squared over r. So now we're ready to go about solving Newton's second law for uniform circular motion, and we just have to remember that the acceleration in uniform circular motion takes this very special form, which is related to the constant speed and the radius. And of course we also want to remember that the direction of the acceleration in uniform circular motion is directed towards the circle. That's why we call it centripetal. Alright, great. This has been uniform circular motion and centripetal acceleration. Thank you guys for watching, and I'll see you next time.